Okay, so let me explain what we mean by concavity. And the idea is concavity is how a function, how a function is changing as far as its shape. So the idea is concave down kind of looks something kind of like this. Concave down is you have a graph that might be doing kind of a U shape going down, kind of like that. It also might just look something kind of like this, okay, or it also might look like something like that. Okay, those are kind of the three key shapes. That's a reasonably good thing to write down somewhere, guys, seriously. Concave down, kind of, those are the way the shapes look. You can kind of think of it as a U shape going down, or like half of a U shape like that. And then concave up, this is also a good little thing to sketch on your notes. Concave up, you can have kind of like an up U shape, or half of one, going like that. Okay, so I kind of think of concave down as a frown, okay, sad. It's a sad face, or half of a sad face. Then I think of concave up as a happy face, okay, like kind of like that. Okay, so you'll see me draw that diagram quite a bit. Well, what it means from calculus is this. So this is what you got to wrap your head around. Okay, first of all, when you're concave down, like here, the slope of the tangent line is, right now it's positive, isn't it? You have a slope, but what's happening is that derivative is changing. Remember, a derivative is a slope of a tangent line. Right now, that tangent line is steep. That's a big tangent line because it's steep. But what's happening is that tangent line is getting smaller. The value, the slope of my tangent line is getting smaller. Does that make sense? Okay, so that tangent line is changing. So what this says is the derivative is decreasing. Okay, my tangent line is the derivative. The value of that derivative is decreasing. Big positive number, and then eventually it's getting close to zero. Does that make any sense? A derivative can change too, all right? And then concave up is kind of like this. And one thing I want to kind of show you on here is the derivative right here is kind of big, and the derivative when you get out here is small. Okay, so the derivatives are going from big to small there. But on concave up, it's backwards. The derivative starts off small. If you look at this tangent line right here, that's a small tangent line. But what's happening is that tangent line is getting steeper, so it's getting bigger. So you're basically, you can do a rate of change of a derivative, and that's what's happening. Okay, so think of concave down as the derivative is increasing, whereas concave down, since you're going from a small slope to a big slope, then it's increasing. Does that make any sense? Remember, I'm talking about how the tangent line is changing. That's the idea. So this is the definition of concavity. This is just saying you're concave up on an interval, and again, that's an open interval whenever the derivative is increasing. So you know how to find where something's increasing. Okay, and then it's concave down on an open interval a to b wherever that derivative is decreasing. So we're measuring how the derivative is changing on concavity. Okay, an inflection point is just going to be a place where the concavity changes from up to down or down to up. Okay, like that. So for instance, you might write something like this. If you had a graph that kind of looked like this right here would be what we call an inflection point. That's a good little sketch to make. And what's happening on this is you're concave down there, and then you're concave up there. So wherever the concavity changes from one to the other, then you would have what you call an inflection point. That's a point on the graph where the concavity changes. So that's kind of what concavity is. Now what we're going to do is I have to introduce this idea, because since you're looking at how the first derivative changes, well then you got to do a derivative of a derivative. Well, the second derivative you can do just means do a derivative twice. So this is the symbolism you need to get comfortable with, is if you have the double prime, that's second derivative. Leibniz notation, you're used to seeing dy over dx. Well, if you have d2y over dx2, that's a second derivative. Those aren't exponents, that's just the symbolism that you're doing a second derivative. So the idea is once you take a first derivative, you can take another derivative, and in theory, you can take derivatives over and over again. Like in my Calc 2 class, there's times when we have to work with 4 or 5 derivatives to do certain things, okay? So that's the idea. In this class, probably the second derivative is about all you're going to need to know how to do, okay? As high as you'll need to go. Okay, an example of a second derivative would be this, and this is also a good thing to write down, is like you learned this, like the first derivative can be thought of as velocity. We learned that a little bit, okay? It's speed, okay? Now let me ask you this. So that's the first derivative. Okay, the second derivative would be how velocity is changing. So I want you to think about that for a minute. You're driving in your car. Hardly ever your speed is the same. Just what happens to your speed? It speeds up and slows down. How do you measure how speed is changing? It's that gas pedal, right? You press the gas pedal, what happens? You accelerate, okay? You press the brake, what happens? You decelerate. So basically, the second derivative would be acceleration, okay? That's just something that in physics that we use. It's how velocity is changing, so it's a acceleration, okay? And then you can measure how acceleration is changing. You know what they call that? I call that jerk, okay? I saw this stupid t-shirt that said this: don't be a this. Only a math teacher would laugh at this. It says don't be that. Well, the third derivative in physics is a jerk. So it said don't be a jerk, okay? All right. All right, let's look at kind of this diagram. I want to just kind of go over that, and then we'll start crunching some of this stuff out. So you want to kind of make sure that you're comfortable with these different things. What's happening on this one is concave down is kind of like the frown right there. Then the concavity changes to up. That's like the happy face. So this would be your inflection point. That inflection point typically occurs, that's saying where the second derivative is 0. Okay, so that's changing. So that's one possibility. Another possibility is you could be concave up through the whole interval. Now you might have the second derivative being 0, but it's not an inflection point because the concavity doesn't change. Inflection points only occur where there are points on the function where the concavity changes. And here's another example. That would be concave up, okay, for a while. Then it would change to concave down, like that. That's like a smile and then a frown. But what would happen on this one is the second derivative would not exist because there's a vertical tangent line there. Okay, so you can have that sort of situation. Okay, that is an inflection point, though, because an inflection point, what's it telling you? It's just telling you the concavity changes. Okay, does that make sense? Okay, and then the last situation would go like this. You could be concave down, then you could change to concave up. You could also have the second derivative would not exist because of that sharp point being there. So it would not. So it would be inflection point is always going to be someplace where the concavity changes, but it's got to be a point on the graph. Yeah.
So it says concave down on the right side. Is that supposed to say concave up?
Oh, no, it is concave down. I'm wrong, okay? It's concave down for the whole way. Both of those shapes are concave down, okay? And what's happening is that's kind of like you're frowning. That's half of a frown. That's the other half of the frown. Now, what's technically happening on concavity is the slope of the tangent line is decreasing. So right now, you've got a tangent line that's almost 0, but then it's getting into smaller negative numbers like that. And then right now, you have a positive tangent line, but that slope is getting smaller. So through that whole thing, the tangent line is getting smaller. That's what's happening. So that's concave down the whole way like that. So the concavity did not change, so there's not an inflection point. Okay, here's your test for concavity. You can use the smiley and frowny face to help you remember this. So if you want to find where something is concave up, you just find where the second derivative is positive. If you want to find where something's concave down, you look at where the second derivative is negative. So I use this. This will help you remember this. You can also add this if you want to. You can put a little F double prime tattoo on the cheek, and that will help you remember that it's the second derivative. Okay, same thing here. Got sad eyes, concave down. That's how you remember that then. Okay, all right, I saw that in a book years ago and thought that was pretty clever. It's stuck with me forever. Okay, all right, and then inflection points are going to be just places where the concavity changes. Okay, but you do have to have a point on the graph. Okay, and let's look at, we're going to go to this example 1. This is kind of one last illustration. This is pretty important. This kind of shows you the 3 ways that concave up can look. It can be like a happy face, part of a happy face, and then you got the concave down like that. That just kind of tells you what's going on this. This one is saying the function what's happening on this one is your concave down or up. Sorry, you're concave up, but you're decreasing. So this one would be concave up and decreasing, and that's a good thing to write down. This one would end up being just concave up, and then it would go from increase to decrease. Okay, then this one would be concave up, but the graph would always be increasing. So those are the possibilities that you have. For concave down, this would be concave down, but the function would be increasing. And then this would be concave down, but the graph would change from increasing to decreasing. And then the last one would be concave down, but you're decreasing the whole way. Okay, does that make sense what I'm saying?
The second one, don't you have it opposite?
The second one, you have.
Which one?
You have it opposite. It should be decreasing.
Where? Which one? A, B,
C, B.
Oh, yeah, I do. Okay, doing it kind of too fast. Yeah, that's concave up, but what you're going to do there is you're going to go from decreasing to increasing like that. And then you'd have like a minimum there on that. So those are the possibilities that you come up with. Okay. Now we're going to go ahead and start working on some functions, and that'll kind of help you hopefully begin to put this together a little bit. So if we go down to this example 1, what we're going to do is we're going to do everything. We're going to go ahead and do increase, decrease, mins and maxes, and then we're going to add in the concavity here. Okay, so on this, the first thing we want to do is we're going to work with the derivative. So if I ask you to work with concavity, you need to go ahead and get the first 2 derivatives. So it goes like this. The first derivative you know how to do. What is that? 20x to the third minus 60x to the second. Okay, now you haven't done a second derivative yet, but it's still the same thing. You just do the derivative of the derivative. So what is that?
60x to the second.
60x to the second minus 120x. Okay, and see, you do increase, decrease, you're working with the first derivative, but when you're working with concavity, that's when you're working with the second derivative. Okay, so we're going to go ahead and kind of focus on the first derivative first, then we'll focus on the second derivative. Okay, so what you do is, you want to find your critical numbers, okay, for the first derivative. We're just going to focus on the first derivative to begin with. So we got 20x to the third minus 60x to the second, and set that equal to 0. So we're going to do a sign chart for that and kind of get this out of the way. Okay, how does this thing factor? You can take a 20x out of x squared out of that. So you want to go ahead and take 20x to the second out. And if you do that, you would just have x minus 3 like that. Okay, now most of the time when you factor, you can do the critical numbers in your head. There's 2 critical numbers. Do you know what they are? 0 and 3. Okay, because what you're really doing is you're doing 20x squared equals 0. You solve that equation, and then you're doing x minus 3 equals 0. So you're going to get 0 and you're going to get 3 as your critical numbers. You do it in your head most of the time. Okay, let's do a sign chart like we did before for increasing and decreasing. Okay, let's get this out of the way. Okay, so what you're going to do on this is you would have 0, and the other critical number is 3. And what we're going to analyze is we're going to analyze the first derivative to see where we're increasing and decreasing. Okay, so what I recommend you do is work with the factored form of the derivative because I think it's easier to process in your head. And when you start practicing this, you'll start getting to a point where you can do these sign charts pretty quickly in your head for the most part. Okay, all right, give me a test point below 0. You read my mind, that's what I thought. So we're going to do 20 times negative 1 to the second times negative 1 minus 3. Okay, and all you care about is just get whether it's positive or negative. In your head, can you do that?
Negative.
It's negative, yeah, because it's 20 times positive 1 times negative 4. So positive times positive times negative. So that's going to tell you that the function is going to decrease like we worked on today. Okay? A number between 0 and 3, let's go with 1. So we're going to do 20 times 1 to the second times 1 minus 3. What's that?
Negative.
That's negative, because that's 20 times 1 times negative 2. It's also negative. So that means the function's decreasing. Okay? Take a number bigger than 3, like 4. That's going to be 20 times 4 squared. 4 minus 3, that's positive. Okay? That's it. Now, yeah, all I really want you to do is just write down, what you're plugging in, and you can get the final answer, but you can just get the plus minus like that. So that means the function's increasing like that. Okay, so let's write our intervals then. So when we write the answers, we're going to be increasing from where to where?
3 to infinity.
3 to infinity. How about decreasing?
Negative
To 0, then?
0 to
Yeah, I'd break it up into 2. I like that. Now, graphically, I already put a graph on your handout, I think, but the way this graph would go, we've seen this before, is you would be decreasing, then you would level off, because you have a tangent line that's equal to 0 for a slope, and decrease some more, level off, and then be like that. And that's what that graph that I put on your paper is doing. You can tell what it's going to look like. Okay, so that takes care of that. And would you have a minimum?
Yes. Yeah.
At 3. You have a minimum there. So we're going to just say local minimum x equals 3. How about a max? No. Okay. Now, what we're going to do next is we're going to work on the concavity. That's what's new. Okay, so that's how you do the increase-decrease like we've been working on today. So now the next thing we want to do is we want to do a sign chart, but now you want to write down your second derivative, which is 60x to the second minus 120x equals 0. So you've got to find critical numbers for the second derivative also. And you do this the same way. What is your factor on this one? 60x, okay. Right, so if you do that, you're going to have 60x, and then that's going to leave you with x minus 2 equals 0, right? So what are the answers to that equation? 0 and 2. Again, most of the time you're going to be able to do that in your head, so that's 0 and 2. Well, what you do is you start over again with a brand new sign chart, and this sign chart is going to tell you how your concavity works and your possible points of inflection. So what we'll do here is we'll just look at 0 and 2. And then we'll do test points, and then we're going to plug the test points on this into that factored form of the second derivative. Okay? So let's use, like, say, start with -1. Do a test point there. So what you're going to do is 60 times -1 times -1 minus 2. What is that?
Negative.
It's a negative times a negative, so it's positive. Yeah, this is really 60 times -1 times -3. It's 2 negatives, so that's going to be positive. So what that tells you is, what does it tell you about concavity? You're smiling, concave up. Okay, don't forget that happy face, okay? All right? Okay, so we'll just write a note to ourselves that we are concave up right there, okay? Then we want to go between 0 and 2. Let's go with 1. Again, plug that into the second derivative that I got highlighted in blue, so that's 60 times 1 times 1 minus 2. What's that? Positive times a negative is a negative. Good. That's just 60 times 1 times -1. What does that tell you? You're sad, exactly. Concave down. Okay, good. I remember that happy face thing. Okay. All right, then we go to 3 as the next test point. Plug it in. You're going to have 60 times 3 times 3 minus 2. What's that? Positive. Now, by the way, the signs don't always alternate. Sometimes students just think that they always alternate. They don't. You've seen them before where you'll have plus, plus. You could even have plus, plus, plus everywhere. It's possible. So you never know until you try that. So what you would have conclude then is now you know your concavity. So your concavity is going to go like this. Concave up is going to be in these two places, so you just write an interval. So that's going to be negative infinity to 0, and then union, the next place is going to be 2 to infinity. That's where that happens, okay? Concave down is going to happen from 0 to 2.
So what about the first when we don't find the concaves of the first part?
Well, the concavity is a brand new sign chart. Okay, so what you're doing is you're working with the second derivative in order to find it. So if you look at, this is the graph of the function. I went ahead and just put this in my calculator and gave you the graph. So what we're doing is we use the second derivative to analyze the concavity of the function.
I got you.
Okay, we use the first derivative to analyze where it's increasing and decreasing. Okay, now points of inflection. Does the concavity change? Yeah, okay, there's going to be one point of inflection at 0 because it goes from up to down, and there's another point of inflection at 2. Now we have to get points, and what we're going to do on that is we've got to get the y values. So the first point of inflection is 0 comma something, and then the second one is 2 comma something. And let's do this without a calculator. You can graph that on your calculator and get it. But what you're doing on this is you've got to go all the way back to the function because you're finding function values. Let's go ahead and crunch that out. If we need a calculator, we can do that if the numbers get kind of big, because sometimes they can get kind of big. So we're going to do f of 0, which is pretty easy to do. Okay, that's just 5 times 0 to the 4th, 20 times 0 to the 3rd. If you can do something like that in your head, you can. So one of your points of inflection is 0, 10. Okay. The second one, you do f of 2, so that's going to be 5 times 2 to the 4th minus 20 times 2 to the 3rd plus 10. Okay, that's 5 times 16, 20 times 8 plus 10. Let's see, let me see if I can do this one in my head. That's 80 minus 160 plus 10. That's negative 80 plus 10. I'm doing that fast, I realize. That's negative 70. Did anybody do that on your calculator? Okay, just to make sure. Okay. So that's what you get is you get this down. Okay. Now, I'm not going to do the calculator on this, but I do want you to label a couple of things on this graph here. First of all, why don't you just put like the point 0, 10. Okay, that's an inflection point. The other inflection point is 2, negative 70. And that kind of occurs down in there somewhere like that. Then I'm going to zoom on this kind of big so we can kind of talk about. See, what you do with your graphing calculator should open up everything we did on this problem. Okay, so does this look like it's concave up, then concave down, then concave up? You guys see that okay? Okay, that's a point of inflection because that's where the concavity changed. Okay, same thing here. And let me show this to you. This is also worth noting. If my pen is representing my tangent line, right now that tangent line is below the graph, isn't it? Okay, everything's kind of below. Now when you go there, it just sort of slices through it. Then when you're here, when you're in a place where you're concave down, my pen is kind of on top of the graph. And then right there, it slices through. And then when you're concave up, my pen is sort of below the graph. That's kind of the way I think of concavity, like that. So the inflection points would just be where the concavity changes. Okay, that's a pretty basic one because it's polynomials. What makes them more basic is the fact that the derivatives are easy and the factoring's easy. You see what I mean? When you start getting into logarithms and stuff, it can get a little bit more complicated. Okay, do you guys understand what I did for concavity? Okay, so what do? You do the second derivative's concavity. What does the first derivative do? Increasing, decrease, min, max. That's what it does. Okay, now let's do one with an exponential in it. We hadn't done that yet. Okay, so you'll get into some things where the derivatives are a little bit more complicated. So we're going to do the same thing. We're going to do everything. We're going to do increase, decreasing, analyze the concavity, and figure everything out. Okay, and I gave you a graph, so the thing on that is we're going to, once we get our answer, we'll see if that's matching what that graph is saying. Okay, step one is you want to go ahead and find your derivatives. Okay, so we need to find the first derivative, then the second derivative. Let's go ahead and get that out of the way. Okay, what do you think you'll do on this derivative? Product, real good. The first function is e to the x. Second one's x minus 3. Best way is just start in a product rule where you have first times derivative of second, second times derivative of first, okay? So the first is e to the x. What's the derivative of the second? That's the blue part. 1 plus the second. Okay, what's the derivative of the first? E to the x. Okay, everybody got that? First, derivative of x minus 3 is 1. Derivative of first, e to the x is that. Okay, now let's kind of clean that up a little bit, and that is, we can write that as e to the x plus, I'm going to just bring the e to the x in front of the x minus 3 like that. Okay, now one of the things that you get into is, remember I said factoring is kind of a big deal. Can you factor that expression? You can, okay, so you want to factor it because it'll make the second derivative a tad bit easier, and it will help finding the critical numbers easier. So what you want to do on this, see, this has two terms. This is the place sometimes students run into background issues and don't do so hot on. So you take an e to the x out like that. Well, what would be left? 1 plus x minus 3. Good. Okay, so you got a 1 there. Okay, when you took that out, so you can block that off in your mind, and then what you'd have is 1 plus x minus 3. Okay, then you want to go ahead and just simplify it from there. So the final result for that first derivative looks like e to the x, and then that looks like x minus 2. Okay, that's my first derivative, so that's a real big deal in this problem. Okay, everybody got that? Product rule and factoring. Okay, now let's go to the second derivative. Okay, the second derivative, we're going to take the derivative of what I got highlighted in yellow here. How are you going to do that? Product rule again. Okay, so it's another product rule. So we're going to do, again, the first is e to the x. The derivative of x minus 2 is what? 1. Backwards, you do the second. X minus 2, derivative of first is what? E to the x. Okay, first e to the x, derivative of second. Okay, e to the x is my first. X minus 2 is my second function. Everybody got that? Okay, now let's factor. Okay, so we can factor on this thing just like we did the last problem. So your common factor is an e to the x. So take it out. So you want e to the x, draw a parenthesis. When you take out the e to the x, what's left over? 1 plus x minus 2. Right. Block out that e to the x and it'll help you see that. So that gives 1 plus x minus 2. So that means the second derivative is e to the x times x minus 1. Okay, and I tell you what, if you don't get your derivatives right, of course, the whole problem will mess up. You're just wasting your time. So make sure that you got your derivatives right when you do that. Okay, so now what we're going to do is we're going to do our first derivative test. So let's write down that first derivative, which was e to the x times x minus 2. And then we're going to work with the sign chart on that. And then we'll work with the sign chart on the second derivative. Okay, we'll just kind of do these one at a time, like that. Okay, so what you have to do is you got to find your critical numbers, and that's the reason why factoring is real important on these problems. So before we go to the sign chart, we got to do these two things. You got to set each factor equal to 0 and solve. Okay, so we're going to have e to the x equals 0, and then we're going to have x minus 2 equals 0. Well, this one's x equals 2, obviously. You can do that one in your head. So that would be one of your critical numbers right there. Okay? Now we've got to think about e to the x equals 0. This shows up a lot here. I want you to think of it this way. If you have a number, e is just a number. It's 2.7 approximately. If you raise it to any power, the question is, will you ever get 0? A lot of times students don't understand this. I want you to think about this. If you take any positive number to any power, you know what happens? You always get a positive number. If you don't get that, you will now, I think. What if you had 2 to the 1 first? That's 2. 2 to the second, 4. 2 to the 0, 1. 2 to the negative 1, 1/2. Still positive, right? That's 0.5. That's a positive number. 2 to the negative 2. 1 over 2 to the second. It's a fourth. It's still a positive number. The point is, anytime you take a positive number to any power, you get a positive number. So this never happens. That has no solution. Okay, that's a place right there a lot of times students don't understand. Now, let's say that you didn't know that. If you didn't know this, what we have learned how to do is in an equation like this, we've been doing a logarithm of both sides. That's what you've been doing, okay? Then you've been learning to bring the x down, so you'd have x ln e equals ln 0. You know what happens? The ln of 0 is undefined. So you would probably figure it out then. But you don't need to go there. You need to know that a positive number to any power is always positive. That's super important. Okay, so that means we only have one critical number, so that means now we're ready to do our sign chart. Okay, so what we want to do on this is, again, we're going to go ahead and draw out our number line here, like this, and then we just divide it up. We got a critical number, x equals 2. Okay, and in the original function, x can be anything, okay? You can take the domain of this function as all real numbers. So we need to plug in to our first derivative right there. So let's just use test numbers. I like using 0 because it's easy. So we would have e to the 0 times 0 minus 2. Positive or negative? It's 1 times negative 2, so what's that? Now work it out if you have to. What does that tell you? That tells you the function's decreasing. Remember, we're working with the first derivative. Okay, take a test point bigger than 2, like 3. Then you would go e to the third times 3 minus 2. What is that? That's positive. Because e to the third's positive. So you just got a positive times a positive. So you got that. So that means the function's increasing. Okay. What does that tell you about max and min? You have a minimum, right? Okay, so you can kind of, over that sign chart, you can say, okay, it's decreasing and it's increasing. So that means we have a local minimum there, okay? So let's fill that out, and we'll do the concavity, and that'll finish us up here. Okay, so it looks like we're increasing from where to where? 2 to infinity, decreasing from negative infinity to 2, and then we have a local min at, let's just write x equals 2. Do we have a max? Okay, so we got that. Now let's go on to the concavity to finish up. Okay, concavity, well, you just take the second derivative and you still do the same thing. Okay, it's already factored, so you set e to the x equals 0 and you set x minus 1 equals 0. Well, obviously one of those critical numbers is x equals 1. What did we just learn about e to the x equals 0? It doesn't have a solution, okay? There's no solution to that. So that means your only critical number on this is just going to be 1. So again, we just can draw a number line and do our sign chart. So we got x equals 1. And then again, you're going to plug test points into that second derivative now, which is this thing. So if you do that, we can use a 0. So that's e to the 0 times 0 minus 1. That's 1 times negative 1. What does that tell you about the concavity?
It's
Concave down.
You're sad. Okay, so it's concave down. Okay. Now do a test point bigger than 1, say like a 2. Go to your second derivative. You would have e to the second times 2 minus 1. That's positive, isn't it? Okay, so it means you're concave up. Good. So then you're ready to put it all together. Okay. So what we would want to do here is we can write our answer now based on that sign chart. So concave up where to where? 1 to infinity. Concave down? Negative infinity to 1. Okay, do you have a place where it's a point of inflection? Concavity changed. Where's the point of inflection? At 1. Now, if you want to get the y value, which I want you to do, we'll go ahead and do that to wrap it up. So that's your point of inflection like that. Now, if you want to find the y value for the point of inflection, tell me where you go. Way back the original. So the original is what, e to the x times x minus 3. Okay, so what you want to do is plug the 1 in. So you want to do f of 1. So that's e to the first, 1 minus 3. I'm just going to leave e in this. So that's e times negative 2. Just write it as negative 2e. That's good enough. That's best. That's the best way to write it. That's the exact point of inflection right there. Okay? If you went to your calculator, it's going to give you a decimal approximation of negative 2e. So that's it. The whole problem's done. And if you kind of compare what we did in that problem with the graph I provided, it's got everything that you would expect to have there. The concavity changes and increase, decrease works the way it's supposed to. Okay? Okay. All right. So we'll do this third.